Hello, welcome to part 3 of Dynamical System. Now try to generalize, most of the dynamical system that we have. So, why it is important to understand especially the coefficient for your states, all right, your present states. Because it's like this. If let's say you have a dynamical system, sometimes when this dynamical system, when you detect the behavior of the system, sometimes you can see, oh, this behavior of the system fits just nicely. It fits perfectly nice. According to our feed data. So it is a good thing, right? But in other case, there are some wild variation. What does it mean by wild variation? Especially true if you have different initial values. Different initial value. For example, like if you're familiar with a uh, uh, paintball, I'm not sure you're familiar or not, but by the end of the day, meaning that if you have a very slight value of one particular system, slight meaning that let's say your starting point is 1.01, and then the next starting point 1.02, for example, is quite small, right? The initial condition is quite small, but if you run this initial condition with the same state of your dynamic system, by the end of the day, your solution is completely wild, completely different than your what you have previously captured or get from your earlier initial condition. In that sense, earlier meaning that 1.01, later you have 1.02. I'm not talking about the changes of the dynamic system. I'm talking about the changes in initial conditions. That is what make things a little bit more interesting about dynamic system. That's when, for example, when you heard about Lawrence butterfly. If you're not, then you can have a look about this. Meaning that Lawrence butterfly, for example, I give you a little bit of a brief ideas. It means that that's why we cannot predict the weather changes, the weather system in more than 5 years. 5 years, of course, not more than 5 years, but not more even 5 days ahead of time. We cannot do that, all right, because there are two involved with the initial conditions that we have, because the weather system um, acts in a dynamical way. All right, the fluid dynamic act in a dynamical way. So you cannot make any assessment in a long term. You can only make assessment in a very short term only. So what Lawrence butterfly identify, it says that if let's say you have a butterfly, and then the butterfly, it flip its small insignificant wings, right, in the, let's say, Brazil. You understand, when you flap a butterfly wing, it is very insignificant, isn't it? Because it is just a butterfly and it's very small. And when you flip your wing, meaning that the disturbance in your original system is very small, isn't it? Because it's just a flap of wings of a butterfly. But nevertheless, this particular small disturbance in your initial condition, it may put the weather system into a very volatile behavior, and then this particular flap of a wing of a butterfly can cause a hurricane in the Jakarta, for example. So that is the idea of Lawrence butterfly effect. If you notice on that, there are even movies talking about this. But I'm not sure whether you watch that or not. But that is the idea. All right. So we show you some of the different example of linear dynamic system. Let's say you have this system, a simple system as previously noted. But this one is more general. All right. If let's say you have just a simple an plus one equals to r an, it is a linear. dynamic system. It does not deal with non-linearity, meaning that you don't see any quadratic form, cubic form, and so on. Okay, it's just a plain linear system. And then you have a constant. Even though this is a very simple system, but you will see later on why it has different behavior throughout the system that you consider. Okay, so let's say we develop a little bit, construct a little bit. What can we talk? How best we talk about this in a long term? Okay, so in this case, okay, you can see when you start to look for pattern, okay, when you start to look for pattern, you cannot run away from starting from the very beginning, right? So meaning that you have A1, A2, A3, and A4, for example, okay, and if you notice, once you develop slowly, okay, you start to see the pattern emerging from your R, okay, instead of you just have R. If let's say you readjust your R into A, okay, so meaning that your A1 is just simple RA0. Okay, that one is clear. But when you have A2, meaning right now your A2 is equal to RA1, and then you know A1 is just your RA0. Okay, meaning that now you have R square instead of R. Your system now is a little bit, oh, it's a little bit different, right, compared to your previous system. And then when you consider A3, your R becoming starting to grow again. It becomes to R cube. And then A4, your R now it becoming to R to the power of 4. And then once you notice this pattern, okay, when you do the conjecture, okay, that's what it means by conjecture. Okay, so once you do a conjecture, you can sense what happened if let's say I have K, okay, K state, okay, K state meaning that I just put the deduction from my A1, A2, A3, and A4 until AK, and then I notice my system now only becomes a simpler system without a future state and the present state, but only deal with an initial condition, which is your A0. Interesting, isn't it? Okay, so now your case right now, you don't have n plus 1 anymore. You only have ak equal to r to the power of k multiply your initial condition. All right, which is a naught. Okay, so right now, you can sense that oh, actually this one is a little bit easier for you to solve, right? Because right now if you have initial condition, then that's fine, isn't it? All right. So that is how we solve things. All right. Okay, so the test of conjecture just another way of you to solve things. All right. So if let's say you try to adjust a little bit, your results can become r to the power of n plus 1 a 0, or the initial condition just equal to rn to the power of 1. This is just like you test a little bit, okay, to make sure that oh, that is my assumption now is correct. Okay, so now it becomes to the theorem. Okay, I show you this theorem because later on this discussion, okay, we are also dealing with quite a lot of different solutions, for example, and you can see the solution. Suddenly you have the equation, but actually the equation coming from the interrelated information in the previous segment. Okay, so if you have time, you can scrutinize a little bit and you can construct. Then you are able to find the solutions. Okay. So it's not that difficult for you to derive. Okay. So for example, this theorem is easier. The solution of a linear dynamical system, linear earlier, an plus 1 equals to ran, where your r is any non-zero constant, is like this. This one is the one you derived earlier, okay? And your a naught now is any given initial values, okay? And then we move forward to see whatever happened, okay? Because dynamical system, we actually more focus. We want to know the behavior in the future or in a long run behavior, okay? So what happened in a long run with this particular linear dynamical system? where your r is constant. Okay, so this is why it becomes more interesting. As you can see, your r now is different. The different type of r will reflect in a different system altogether in a long run. Okay, for example, if you have a constant r, sorry, I mean the constant is also r, but if you have a specific value of r, let's say your r is 0 and 1, okay, it's different. Okay, if you have r equal to 0, you will have a constant solution. Your equilibrium value at 0. What do you before this? Maybe I should highlight what does it mean by equilibrium if let's say you already forget from your previous study. Okay, equilibrium point is a point where by the end of the day you get one particular solutions. Okay, meaning that suddenly if you do all over again, you do the same system together in a long run, by the end of the day it will converge into something that gets you into the equilibrium, the point where you are able to capture the value inside this particular convergence value. Okay, so that is the idea of equilibrium. Okay, and then if let's say your r now becomes 1, then your long-term behavior, your all initial values are constant solutions. What about if your r less than 0? Your value now becomes an oscillations of functions. What if you have less than 1? It will decay. Whatever happen if you have r greater than 1? It will grow. Okay, the growth without bound. Okay, so one of the example earlier that we talked about the um, saving, okay, saving accounts, okay, the one that we have earlier, you notice our R, if you forget, I refresh you with the values. Okay, you notice our R is actually 1.01. Okay, I recap back in case you didn't you didn't watch the previous video. Is in the, I think, part 2 or part 1. Okay, video part 2 or part 1. Okay, our R is 1.01. Okay, so 1.01 is actually the long term behavior of that particular system is a growth without bound. Okay, meaning that if let's say you put money and you didn't take out the money until the end. Okay, let's say you die, okay, in 35 years old, sorry, 35 years in time, and then you didn't do anything with the money and the money does not froze. Okay, then the money will grow abundantly. Okay, I think you understand the concept abundant of your wealth, right? So that is why it grows abundantly because your R follow this system. Okay, it will grow without bound. All right, so this is the concept. Okay, if you notice on the first one, okay, this is the condition. This is something like our investment. All right. If your R greater than 0, it will grow without bound, meaning that, it looks a little bit like an exponential form, right? Even though it does not reflect strong exponential, but by the end of the day, up until here, for example, you notice significantly it will grow accordingly. And then once over here, you can imagine it will grow abundantly without bound. Okay, the same thing happens for this one. Okay, the concept is the same. It's still exponentially driven. Okay, but the difference is on your A. Okay, but we do not focus on A at first. We just focus on your R. Okay, whatever happen if your R is in between 0 and 1, okay, your value it becomes like this. Okay, you can see over here. This is what it means by decay. By the end of the day, it will go up until here. Okay, so this is more or less if you notice the experiments with culture, for example, not culture in the social forms, but culture in your petri dish. So this is how your decay exponentially, for example. Okay, this is what it means by this. Okay, the same thing happens for your D, but it's just the method of difference A. And then this is the example of oscillation. Okay, oscillation meaning that it's like a sine and cosine values, right? It's like like this. So that's what it means by oscillation. So you can see you can see the same system, but with different r, your graph will becomes completely different. Okay, that's why people enjoy working with dynamical system. Okay. Now, now we proceed to the next system. Okay, so this one is quite similar to the previous one. Okay, but now it involved with another constant. Okay, so the difference with the previous lesson is just this. Okay, you notice we only put one particular constant, but the concept is completely different. So that's why it's like sometimes you get overwhelmed with these problems. But if you dig deep and look very carefully about your system, and then you can see, oh, actually, this is the behavior. This is normal. The behavior is normal, and then by the end of the day, you can predict, especially if you're using the simplest version, not saying MATLAB or that one is also easy for you to solve. Okay, but if let's say you are only using Excel, you can also solve certain data. Okay, we're going to discuss more about the Excel formulation in classroom. Okay, so this is example. A number A is called an equilibrium value or a fixed point of a dynamic system. Okay, if your AK equal to A for all K. Okay, that is your AK equal A is a constant solution to the dynamical system. All right. So basically, if you look at theorem 2, actually how you can derive your A equal to B over 1 minus R, that one. Okay. As I mentioned earlier, it's very similar to the way we construct or we derive the solution in our theorem 1. Okay, so you need to derive a little bit further, starting from A1, A2, and so on, and then realign a little bit, and then by the end of the day, you will get your A, just as it is, given the definition at the top. Okay, I hope you can try the derivation for your theorem 2. Okay, straightforward. Okay, what about the long-term behavior? So you can see over here, your R, uh, you put extra B, okay, this one, but this one, the value for your R and the long-term behavior is completely different than your previous slides. Okay, you can double check your slides earlier. You can see it's different. Your earlier R less than 0, if I'm not mistaken, it should decay, but right now you already have a stable equilibrium. Okay, and then for R later greater than 1, you have unstable equilibrium. The previous one without B, you have, if I'm not mistaken, greater than 1, it will grow. Okay, your value will grow abundantly. Okay, unbound. Okay, but this one you have unstable equilibrium and so on. Okay, so this is the solutions. For the dynamical system, your AK right now, okay, previously you only have, okay, I show in case you get confused. This one when your AK equals to A, right? But this one, if let's say you have a more general terms, now your AK just equal to R to the power of K, C plus B minus B over 1 minus R. Okay, so C is just any constant. All right. Again, this one is also you can derive a little bit tie with different solutions previously, but you will be able to derive this, inshallah. Okay, so I hope you enjoy the video and I hope you understand what is dynamical system, and how why certain why certain model in dynamical system will produce different kind of results, and why dynamical system is something that is very interesting for us to see more of it. Okay, so I just want to recap a little bit. You can the most important part of dynamical system is especially if you are familiar or not. Okay, many people do a predator prey model. Okay, that one is a completely a dynamical system. And then the investment vehicles, all right, compound savings, that one is also deal heavily on difference equation, all right. Especially right now, right now in a COVID form. Okay, so because you know it is a the state of development of the virus. Okay, the way people getting infected. Okay, you can see the way people getting infected, that one is a state. Okay, it's a state space. Okay, this today, and then one particular individual, when you talk about R naught, for example. Okay, um that's why sometimes when people start to see about the difference of R. Okay, if let's say you have R naught equals to 1 point something. Okay, meaning that the ability for one particular person to infect uh, 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 to be able to carry, okay, to be able to affect other people's is more likely than none. Okay, meaning that depending on your R, sometimes if your R is a little bit high, meaning that you are able to affect four people altogether in this particular stage. If your R is less, then it will affect, let's say, 1 to 1. Okay, so these are all the states development. Okay, that's why it's very very interesting to look at dynamical system. Okay, but let me remind you, it is quite extensive work. Okay, it's not just one size fits all model. Every model is different. In particular, your equilibrium point and the way you see the behavior and the pattern of the conditional situation is different. Okay, so again, you have to look carefully and study more extensively on dynamical system. But by the end of the day, it will help you solve a lot of many things. Okay, so I hope you enjoy the whole three parts of dynamical system. And then I'll see you guys in the next feature. All the best.